This video is meant to introduce some additional features of parabolas. We've previously studied parabolas and we know that they are U-shaped graphs. We know that they have a vertex, and we also know they have an axis of symmetry that divides the parabola in half. And the parent function, of course, for our basic parabolas that open either up or down would be just y equals x squared. But there are some additional features that are especially useful when we take a look at some real-world applications of parabolas. And it turns out that parabolas also have a fixed point, very much like the ellipses and the hyperbolas that we've already studied. They have a fixed point which is called the focus, and it lies inside the parabola, and it's also on the axis of symmetry. So the focus, for example, would be somewhere here, on the axis of symmetry, and inside the parabola. But in addition to a fixed point, parabolas also have a fixed line. So the fixed line is called the directrix. And if we were to measure the distance from the vertex of the parabola up to the focus, and then go that same distance the other direction along the axis of symmetry, the other direction from the vertex, we would land on the fixed line, and this fixed line is called the directrix. So all parabolas have both a fixed point, which is called a focus, and this fixed line, which is called a directrix. And you'll notice that the directrix is perpendicular to the axis of symmetry. Now to locate the directrix, again, we have to measure the distance from the vertex up to the focus, and we often call that distance p. And if we traveled the same distance p, the opposite direction, that's how we would locate the directrix. Now, we'll be discussing this value of p in more detail in just a second. P, it turns out, can be positive or negative. So when we're talking about it as a distance, it's important that we put it in absolute value. So we really define the absolute value of p as the distance from the focus to the vertex of a parabola, or the distance from the vertex to the focus, if we want to begin at the focus. And then that's also the distance from the vertex to the directrix. So it turns out there is a special relationship between the focus and the directrix and all of the points on the parabola. So if I were to pick any point on the parabola and measure the distance to the focus, and then also measure that distance down to the directrix, it turns out that these two distances will always be equal. So again, picking any point on the parabola, measuring the distance to the focus and the distance down to the directrix, those two distances will be the same. And this leads us to our formal definition of a parabola. We say that a parabola is the set of points whose distance from a fixed point is the same as the distance to a fixed line. So again, a parabola is the set of points whose distance to a fixed point, which is called the focus, is the same as the distance to a fixed line, which is called the directrix. So now, using this definition and the location of the focus and the directrix, we'll be able to derive an equation for a parabola that involves that distance p that was mentioned earlier. So let's start with a new graph. We'll have our xy axis, and go ahead and just freehand in a parabola. So our picture won't be perfect, but it's going to be good enough for us to derive our formula for a parabola. So locate your focus, which remember is on that axis of symmetry. We'll go ahead and label the distance from vertex to focus as the absolute value of p, and then travel the opposite direction, also the absolute value of p. so that we can have our fixed line, which is our directrix. So starting with this parabola, which has a vertex at 0, 0, let's go ahead and pick a point on the parabola. I'm just going to label the point on my parabola point A. And I'm going to connect A to F, distance from the focus to the point on the parabola. Then I'm going to come straight down from point A to the directrix. And I will label that point point B. So now we'd like to go ahead and get some coordinates for all three of these points. So let's start with the focus. Since the vertex of the parabola was 0, 0, we went up a distance of P to get to the focus. Then we can label the focus point 0, P. Now point A was any point on the parabola. That's an unknown. So we'll just label point A as x, y. Now point B, you'll notice point B lies directly underneath point A. So it shares the same x value as point A. However, we traveled from the x-axis down a distance of P, or absolute value of P, to get to the directrix. And since we went down, we could label the y value then as negative P. So the coordinate for point B is x, negative P. Now, as I stated earlier in our definition for a parabola, we know that the distance from point A to F, the focus, must be the same as the distance from point A to the directrix, which would be from point A to point B. So I'm going to label those two line segments as congruent. They have the same length. Therefore, we know the distance from A to F must equal the distance from A to B. And luckily, we have a distance formula that lets us compute the distance between 2 points on a plane. So let's go ahead and remind ourselves of the distance formula. So the square root of x sub 2 minus x sub 1, the quantity squared, plus y sub 2 minus y sub 1, the quantity squared. This will calculate the distance between any 2 points. So let's start from A to F using our distance formula, and let's calculate that distance. So starting with point A, that would be the quantity x minus 0 squared plus y minus p squared. That would be the distance from A to F. And now that distance must equal the distance from A to B. So using the distance formula from A to B, we'll have the square root of x minus x, the quantity squared, plus y minus negative p, the quantity squared. So now we have an equation here that we're going to manipulate. So first, you might think to get rid of the square roots. So if we go ahead and square both sides, both the left and the right, we can undo the square roots. And then we can also do a little simplifying. So for the left-hand side, x minus 0 squared is really just x squared, plus we still have y minus p, the quantity squared. And that'll be equal to the right-hand side, x minus x is 0, so 0 squared will be 0. And then we'll have the quantity of y minus negative p, which turns into y plus p, the quantity squared. So now let's go ahead and multiply out the left and the right-hand side to see if we can combine some like terms. So x squared plus y minus p, the quantity squared, will change to y minus p times y minus p. Same with the right-hand side, y plus p times y plus p. And now we'll go ahead and multiply. So we'll have x squared plus y squared minus 2yp plus p squared equals y squared plus 2yp plus p squared. And now let's go ahead and try to combine like terms. So you'll notice that if we subtract y squared from both sides, the y squares are going to subtract out. If we subtract p squared from both sides, the p squareds are also going to subtract out. On the left side, I have a negative 2yp, so if I add 2yp to the left as well as to the right-hand side, I will end up with 4yp on the right-hand side. So this leaves us with x squared on the left is equal to 4yp on the right. Now remember, this is an equation for a parabola, so I always encourage you to think back to the parabolas we've already studied. We've been studying parabolas with parent functions of y equals x squared. So we'd like to have y by itself, since this was a parabola that opened up. So let's go ahead and take this equation and let's solve for y. In other words, if we're going to solve for y, we need to divide by 4p. So dividing both sides by 4p leaves us with the equation y is equal to x squared divided by 4p. I prefer to write that as y is equal to 1 over 4p times x squared. So here's the equation for the parabola. This parabola had a vertex at 0, 0, and it opened up. What you'll notice, I hope, is that the leading coefficient here is 1 over 4p. So this would be the same as our previous equation for a parabola, y equals ax squared, one that had a vertex at 0, 0. Remember that a value would tell us whether the parabola opens up or down. It also tells us whether we have a vertical stretch or a vertical compression. So we used to call that coefficient a. Well, now we have another way of defining that leading coefficient. We could call it 1 over 4p. In other words, a is equal to 1 divided by 4p. Now, why would we want to use 1 over 4p instead of a? Well, going back to our previous diagram, remember that p was the distance to the focus, as well as the distance to the directrix. So if we're faced with a problem where we want to know the location of the focus or the location of the directrix, then we'll want to use this definition 1 over 4p as our leading coefficient instead of calling our leading coefficient a.